We're going to finish up our talk of sound and light by talking about color, polarization, and refraction. Humans see in color because we have cone cells in the eye, and each cell is receptive to red, green, or blue light. Now, red, green, and blue light all have different wavelengths, so it does go by the color. So it goes red, orange, yellow, blue, green, violet. Red has a wavelength of 700 nanometers, all the way to purple, which has a wavelength of around 400 nanometers. Green in there at about 550 and blue in there at 470. So, and green in there at 550. Sure, we'll put some yellow in there at about 600. So that's our wavelengths of our visible light colors, and they are different. You have the three primary colors of light, which unlike red, yellow, and green are red, yellow, and blue, are red, blue, and green. These are the primary colors of light. So I have red, blue, and green flashlights in my classroom, and when you put all three of those colors together, they make white light. It's actually pretty fun to combine them. Now, what happens is if you combine, say, red and green together, they make yellow light. If you combine blue and green together, they make cyan, and red and blue makes magenta. Now, I've drawn this triangle because the opposite colors of this triangle are the complementary colors. So if you put red and cyan together, they'll make white light. Blue and yellow will make white light, and green and magenta will make white light. Now, magenta, yellow, and cyan are the primary colors of pigment, as you might recognize from your printer toner cartridges. So light is pretty interesting to play with the colors. Now, the next thing we're going to talk about is polarization. So if you have sunglasses, what happens is you can get polarized sunglasses, and they take away the glare off of things like lakes and cars and that sort of thing. They are really nice. But how they do this is in electromagnetic waves, the electric field oscillates perpendicularly to both the magnetic field and the direction of travel. So light from a typical source consists of waves that have electric fields oscillating in random directions. And this is unpolarized light. So you have electric fields oscillating in random directions. The only thing you know is that they are always perpendicular to your magnetic field that's oscillating and the direction your wave is traveling. Okay, there are processes that separate waves with electric field oscillations in the vertical direction from those with oscillations in the horizontal direction. So that's how we get rid of glare. That's light with electric waves traveling horizontally. And what then they produce a stream of light that has all electric field waves are oriented in the same direction, and this is called linear polarization. So only light on the transmission axis can pass through your polarization lens. All light at 90 degrees to the axis can't pass through. So if you put the same polarizer at 90 degrees to each other, you won't have any light that passes through. So polarization is actually super interesting and neat. I don't know that much about like what materials they use. Which brings us to the subject of refraction. Refraction is the bending of a wave front as the wavefront passes between two substances in which the speed of wave differs. And we need to know some things. Now, you know this happens with light. This is why when you're fishing and you see a fish, it's actually further down than it looks. So it makes it look like it's not quite as, or it makes it look bigger. So what happens is as your light comes in and it hits the water, because it actually travels more slowly on water, it bends a little, and it bends toward the normal because you've gone from air to water, which is faster to slower. If, say, you're going from water to air, it would bend away from the normal because you're going from slower moving to faster moving. And this brings us finally to Snell's law, which is your index of refraction of your first median multiplied by the sine of your initial angle, your incidence angle, is equal to the index of refraction of your second median, your refracted median, times the sine of your refraction angle. Okay, and we're just going to do a couple of problems with this, and really that kind of wraps up light for us. So example number 2. Now on this page I have included some indices of refraction so that you can just find them there on your page. A light ray of wavelength 589 nanometers produced by a sodium lamp, all of that is extraneous information, traveling through air is important, strikes a smooth flat slab of crown glass at an angle of 30 degrees to the normal. Find the angle of refraction. So we have air, which index of refraction is very close to 1. Certainly to those decimal places, that's 1. And then we have crown glass, which has an index of refraction of 1.52. So we're going to solve for our refraction angle. So we end up with theta r is equal to the inverse sine of ni sine theta I divided by nr. Theta r of 1 times the sine of 30 degrees divided by 1.52. That gives us a refraction angle of 19.2 degrees. Does that make sense? Yes, it does. It's going to be traveling more slowly, so our refraction angle is going to be smaller. And that wraps up our physics course. Wow, I can't honestly believe that we covered all of that. At least this way you will have heard all the terms when you kind of cover this again in more depth.